In the second level, the students would become familiar with analog MTI processing, including familiarization with the analog pulse radar, the PPI display, the phase processing MTI, the vector processing MTI, the staggered PRF, MTI limitations, threshold detection, pulse integration, sensitivity time control, instantaneous automatic gain control, the log FTC receiver, the constant false alarm rate, and troubleshooting an MTI processor, troubleshooting the display processor, and troubleshooting an MTI radar system. This level also includes the digital MTD processing, which familiarizes the students with the digital pulse radar, with the PPI display, cell mapping, fast Fourier transform processing, CFAR constant false alarm rate, correlation and interpolation processing, surveillance track while scan processing, and an exercise on troubleshooting the digital MTD PPI processor. To demonstrate the capacity of our processing, I used our target table to have a slowly moving target, so we have something to see on our PPI display. I also added a computer along with the processing interface and its power supply. This processing interface is connected through an Ethernet cable to my computer, but it could also go through the network, so any computer could access it. Now I will need to add my connections. Let's make it simple at first. I will disconnect my motor drive so I'm not hurt by the antenna rotating. So I will need to have my synchronization as well as my PRF into the data acquisition. I will also need my I and Q channel from the dual sampler. So these are my pulses, these are the synchronization, and I also need the azimuth output to know what is the actual direction of my antenna. So now I will reconnect the antenna drive and we'll switch to the computer to see the processing itself. I will now start the LabVolt radar training system software, and it will first ask me which kind of radar I want to study now. Let's select the analog pulse radar. You could also work in standalone mode, but in that case, although you can see the wiring diagrams, you don't have any signals. It's not a simulator, it's really a data acquisition for the radar. So now it's connecting to give me a pulsed signal, transferring information in the data acquisition and initializing. Let's move to a more detailed view of what is on the computer itself. So in the computer, what I see is that I have several tabs that are available here on the top. Let me first close the tab of the system settings on the right. We'll come back to it later. So I can zoom in to see, for example, my analog pulse radar. I can pan into that to see all of the actual connections on the system. I also have the RTM connections here that will tell me what to connect on each place. I have a clutter injection, signal injection on the left. I have my data acquisition in the center. And on the right, I have output signals that I could use with conventional instruments such as an actual PPI display or an oscilloscope. I can also access the details of the MTI processing and the display processing as well. But first, let's take a look at the radar display itself. So now we see there are lots of targets on that. I am very close to a wall, so actually all of this line here is my back wall. We see the studs in the wall. This bright pile here is the actual radar pile itself. This green spot here around 270 degrees is my actual moving target. What you also see right here is me being close to my computer. So we do have intensity modulated radar. We do have fixed intensity, which will go with a threshold. The threshold, of course, could be changed. If I put a higher threshold, I will have some targets that will disappear, which means that I could be missing some of my targets, but also I have less noise to look at. I also have a color modulated targets where the biggest radar targets will be in red and the smallest will be in shades going to blue. When I adjust my distance properly, I can also add range rings. For example, here if I put 6 rings, I will see green indications of the various distances. I can also have a variable range ring, which then I can drag in and out. For example, if I want to measure the distance of that target here, I could see that it is right now at a distance of 1 meter. I can also have a electronic bearing. So now I have both the distance and the angle of what I'm looking at. Now I have a nice PPI display, but I could also be interested in learning more about what is this MTI processor. So if I go inside here, all of the squares are my actual output signals that I'm sampling. But I can also look at the details inside here, and each of the smaller blue dots are additional test points where I can connect virtual probes for my oscilloscope. For example, if I wanted to see my I channel and my Q channel, sorry, that wasn't the right one. See my Q channel, and I'll put my external trigger on the PRF detector here. Now I can launch my oscilloscope, and this looks like a regular scope. I will need to enable my 2 channels. I need to start the refresh on these and decrease the sensitivity until I have something that is acceptable for what I'm interested into looking. So now I see that I have a lot of offset on my signals, so I will go on my sampler and compensate for these offsets. So I see here that I have my early reflections that are in the base, and after that I have the various echoes that are generated by the targets in the system. I will stop the rotation of the antenna, and I will try to aim to a target that is slowly moving back and forth. I will reduce the gains a bit further here. So right now I can see the result of 2 successive PRFs. So let me change the time base here to remove one of them. I will also compensate my origin a little bit. So when the target moves back and forth, the signal will oscillate between the I and Q channels. But the vectorial sum of these 2 signals should always be equal to unity. Other things you could take a look at in the signal path is the Mti processing itself. If I had a delay equivalent to the PRF, then I can subtract the previous pulse, so every static target will be removed and only moving targets will be in place. I could activate the sensitive time control. I could look at the signal after the vectorial summer. I could go through a log amplifier and an automatic detector, or in the linear processing with an instantaneous automatic gain control. I could add video integration and a clamping circuit, and I have access to the circuits up to the output. I could also here control my clutter generation, so I can generate either noise, I can generate interferences, I can generate simulated rain and simulated sea clutters. And the students would see the effects of these on the signal and ways to counter these effects. In the display processor, I can look at various signals that are available as well. This system can also work in digital MTD mode.